All right, guys, Dr. Mom, online professor here. We're back with the Pearson Correlation. So let's think about the Pearson Correlation. And once again, let's just go over a couple steps and then we'll go through the actual formula on how to conduct a real Pearson correlation. So remember, the Pearson Correlation, it actually measures the relationship between two variables that are scale. So remember, they have to be variables that actually lead to numbers like age, income. Now, not gender, that's like a nominal or category, not religion. Has to lead to an actual number. And so for every change in one, it will lead to the change in the other. So in every change in X, it will lead to a change in Y. So anything happens with age, it will lead to a change in your income, right? And so if we're talking about these two different things, what are we truly measuring inside of the actual Pearson correlation? Well, there's a couple things we have to keep in mind before we can do those measurements. Just like if you saw the video on the ANOVA, you have to keep in mind that there needs to be independent observations. In other words, we're saying that when you take a measurement for every person, you should take their age and you should take their income. It should only be measured once per person in both of these categories and never double dipping, never measuring more than once for each person. So there should be independent observations. And if all these characters are independent of each other, you can truly measure how much age is impacting income. But think about it. If you've ever heard the phrase in the Pearson correlation, correlation is not causation, 100% true, because the Pearson correlation only measures one specific thing, the relationship, right? The degree of that relationship. In other words, is that relationship strong or weak? In terms of it being a linear relationship. That's why we have the whole scatter plot up and down, right? X and Y. So when we're looking at it, we're keeping in mind the degree of that relationship. The degree of that relationship is measured on a scale from negative 1.00 to positive 1.00. The closer you are to 0, no relationship. So the closer the measurement of it comes out to be a 0, that means you have no relationship. The closer you are to 1, the more of a perfect relationship. So if we were looking at this as an X and a Y, right, we'd say the closest the dots come together, the closest you'll be to 1. The farther apart the dots are from each other, the closest that you'll actually be to 0. So it's actually a visual representation of this. And that representation is really good to do a measurement of the degree and strength of an actual relationship between two variables. Now, how do you actually mathematically, right, calculate that relationship? Well, if we look at the Pearson correlation and we're measuring things based off of samples, because remember, you never work with the population, you always work on samples, and samples are going to help you understand populations. So if we look at the formula, right, R is rho, in other words, R is the Pearson correlation in its sample, because rho, this capital Greek looking P, is actually in the population, right? So we measure it with R in the sample. And so looking at it, what do we actually measure? We measure in the formula something called the sum product and the square root of the sum of squares of X and the sum of squares of Y. So basically, what's it measuring? On the top, the sum product is actually measuring the covariability, how much these two vary together. And the bottom measures how much they vary independently, the variability of X and the variability of Y. So it's the covariability together versus the independent variability all combined to measure the relationship and its strength and degree and direction, and of course form, in terms of linear, of the relationship of this specific variable. And so this is the first time when I'm talking to my students that I tell them, we're used to seeing a formula within a formula. That's normal. But this is the first time we actually see a formula on the top. There's actually a formula within a formula on the top. The sum product is actually specifically a formula. So you can have the computational, or you can have the definitional. The computational, the definitional, both will get you the same answer for the sum product. One just might be easier or harder for different people to understand. I have a preference. I'll tell you why in a second. And when you see the example in the next video, you'll definitely understand why I have a preference for one versus the other. But either way, I always tell my students you should do both. Why? Because if they both lead you to the same result, then you can use them as checks and balances. If they both give you the same answer, you know your calculation was correct. And yes, you can do this all on SPSS and by hand. You can do it all SPSS by the computer. But when you do it by the computer, you have to understand what it's doing by hand. Because sometimes it's really easy to look at a calculator, punch in the numbers, but then can you interpret the results? It's like I tell my students all the time in the beginning of my stats semester. I tell them it's simple. You can tell a kindergartner, a 5-year-old, a 2-year-old to grab a calculator and punch in numbers. If I ask my toddler, I ask Lucas who's 3, grab a calculator, he knows numbers, 3 plus 2 plus 6 plus 7, add in all these numbers, multiply, divide, and add. And the end result of that calculator is 6. And I ask him, Lucas, what does 6 mean? He looks at me like I'm speaking Chinese. He's like, what? He has no idea. He'll walk off and start playing with something else. Because the conversation and the actual question meant nothing to him. He can't interpret a number unless he understood the process with which that number was obtained. Same thing happens here. So you can use both of these as a checks and balance. And you can use either one of them or both of them combined to see if they led you to the same place so you can understand the result. So if we talk about the computational formula for the sum product seems like the easier one because it's the sum, right? Remember, the sigma symbol means sum. It's the sum of the x scores times the y scores. Remember PEMDAS, order of operations. You have to do this in a specific order. So first you would multiply all the x numbers, all the age, or if you were doing the x and the y with the age and income. You would multiply, right? You would take all of the age times income, age times income, age times income for every person, and then you would add them up, right? So you would do the age times the income, right? Add them up, and then you would have a fraction over here. Sum of age, sum of income, x and y, divided by the sample size. So you would take them independently, the sample size together, because remember, each person's being asked something twice, and then you would have the separate. That is the computational formula. Pretty easy to do. The definitional formula is a little bit longer process, but the reason it's my favorite is because it will lead you to the sum of squares. So let me tell you the formula. The formula for the sum product is simply the sum, remember order of operations, x minus the mean of x times y minus the mean of y. In other words, if you know anything or remember the calculation for the sum of squares in times of getting the variance and standard deviation, these are called the deviation scores. And the deviation columns are what are going to lead you to the sum of squares. So if you're doing this by hand and you use the definitional formula, you're actually halfway through the process to get the bottom numbers you will need for the formula. If you use the computational, you still have to go through this process to get to that process. So for me, I prefer the definitional formula, but either way, this is the process to get the Pearson correlation. And when we talk about our next video, we'll talk about it using hypothesis testing, the 4 steps in a real life example on how to truly use this formula.